This video will demonstrate how to use RiTHM to verify properties in runtime using dynamic polling. Our example is going to be a simple Fibonacci program. As you can see here, the code is basic Fibonacci implementation. We have three comments that RiTHM uses to insert its code. The first comment is for the includes that RiTHM needs. The second comment is for monitor calls, and then the third comment is for monitor code. The second file we have in this folder is the CFG file, which contains the properties that we need to verify. We have three properties: eventually A, and A is that I is greater than 10, always B, and that is I is less than or equal to N, and then always C, and that is F new is greater than F old. If we go back to the source code, you can see that these are the variables in our file. Now let's start running the tool. So we begin by launching our UI. We start with selecting the source directory, which for our case is going to be Fibonacci folder. The output directory is a directory we will create. And then finally the properties file, which is the CFG. You can select here dynamic polling. We have all the configurations that we can do for dynamic polling. We have multiple controllers. We will select fuzzy 1. We'll set the initial sampling period to 1,000 microseconds, and then the maximum might be 20,000. We can set the static buffer size, for instance, to 20 events, and the safety percentage to maybe 80%. Fuzzy scaling factor could be 5,000. Control notification for 5, maximum buffer size of 100. These are all parameters that you can change to control how responsive your controller is to the changes in the events. This checkbox enables us to log the trace and see the changes in the variables of interest. So now we begin by running the tool. So now we have the final processing of the file has been successful, and we have output the files. So now we can go into the output folder. We have a source folder there, and we can see all the files that have been generated. To compile them, we use a command such as the following. So we have loading libraries from the one directory up, and you can see that this is in fact where we have our libgoomf. One directory up from the source. We have two source files that need to be compiled, and then we have three libraries. We have libgoomf, we have librealtime, and libmath. Now we can run our tool. So this error is because we need to set the path for the goomf library. So we do that right now. So the program has been run. We can now check the output. So the output is written to this file. So you can see here that the properties are, as you can see, property 0 is satisfied, property 1 is probably satisfied, and then property 2 is violated. So property 0 is the one that checks for I greater than 10, so that is satisfied, as you can see. If you scroll up, you can see that before it reached 10, it was probably violated, but once it passed 10, it became satisfied. For property 1, it's probably satisfied because up until now, I is less than 30, but then at this point when it's 31 and it's greater, it becomes violated. And then for property 3, which is F new is greater than F old, this will be violated from the start because of this case where we have 0 and 0 in F new and F old. Now, Another form of output that we can see using RiTHM is monitoring the real-time performance of the controller. So we can do this by launching our UI and going to the real-time plot section. Now we can change our program so that it takes some more time and we can see some more response. So we can go down to our Fibonacci code and may set the number of iterations to maybe 30,000. Now we need to compile again and then run. So as you can see here, let's disable coefficient of variation. As you can see here, the buffer utilization is stabilizing, and so is the polling period. The oscillations here are just based on system noise. We can look at the average polling period, which is moving closer towards the average polling period, which is up here. And then we can see the coefficient of variation, which by time will start decreasing once we have a more stable set of polling periods. As you can see now, it's beginning to fall below the 100%. And that is just based on how we have a set of closely distributed polling periods.